Hello, everybody. This is the second team, D years. We have 4 team members. That is me, Charlie, and Charles, who's responsible for illustrating our ETL process, and James, who is going to explaining to you our data serving strategy and our CDC plan. And also Song Yan, who is going to explaining our modeling part. And also we have a DevOps team member who is Lawrence. He's contributing to our whole architecture's DevOps component. So let's right into our project. So today's agenda will be broken down to 5 components. The first part, I will briefly introduce you the background, and then the second part, I will let you know the tech stack of our team. And then we will right into the architecture of our project. And then we have our next steps and FAQ for all of you. The first is our background. Our team's project is called e-commerce recommendation engine because our customer is the supermarket Imba, and its marketing team is aiming to solve non-effective upselling marketing activities. So we will extract our customers' transactional data from our old database and will convert them to useful insight that we will going to recommend products based on our customers' past interactional behavior with us. So let's look at our tech stack. Our whole project is based on, is deployed on AWS. So you can see that we have used IAM, CloudWatch, VPC, Aurora RDS, and so on for our whole project. And our DevOps team will use Terraform to deploy all those resources and the codes of our team to AWS. And in terms of programming language, we use Python, PySpark for Glue ETL part. We use PostgreSQL, Bash, and Markdown. And also in the whole process of our project, we use Jira for project management and code for our code control, and we've created a BI tool that's going to show everybody the output of our e-commerce recommendation engine, and its backend is written by Node and its front end is Angular. And then let's go into our architecture. We have broken down our whole project architecture into 2 parts. The first one is today's main branch. The aim is to get the raw data from our customer, the Imbar supermarket, and then transform them into useful recommendations to our customers. This is the main branch. While the second branch is called the CDC for Business Intelligence Demand, because as we know, our marketing team, they does not only need the recommendations for customers, they also need to capture those customers' interaction behaviors. For example, when the customer have add one product into the cart, and when will the, for example, change to payment, they need to capture those change data for future analytical use. So we've also created a CDC branch to meet their needs. And then let's first talk about our main branch, that is the lower part. Our main branch has broken down into 5 main components. The first part is data storage. The second part is data replica and our recovery plan. The second is ETL part. The fourth is modeling part, while the last is our data serving part. Our DevOps team have offered a VPC for our data storage and data replica because our raw data will come from our web applications and the mobile applications of our customer who's browsing our e-commerce platform to buy our products. And then their data will go inside into our raw database, our RDS from Internet Gateway, and then it comes to our private subnet, and then our data will transfer from our RDS raw database to our replica, and then all the data flow from the database part, to ETL part, modeling part, and the data serving part. So let me explain to you in detail mode of our data storage part. So for our database design, we have considered to perform partition test for more effective queries of our later project, because our data is in large scale and it has a high requirement for ingestion speed, and we also need to consider traffic balancing. So we have chosen range partition strategies among all of those data partition strategies, especially for our two fact table, the orders table, which stores the data of each order of our customers, and then the order product table, which contains over 14 million data of our transactional database. So for our orders table, we choose user ID as our partition key and it will divide the whole data into 5 partitions. The reason why we choose user ID as our partition key is because when we choose user ID, the whole database is distributed in a less skewed mode versus all the other partition keys. And also we can see that its performance comes to a more balancing mode compared to another partition strategies. And also we choose user ID, order ID, and user ID plus order ID as our index. While for order product table, we choose product ID as our partition key and also divide into 5 partitions because it comes from the data balancing and the data skewness test. And you can see that we use Asina to perform this range partition strategy and then divide our whole data structure in a more effective way for future data query purpose. And also, we use Aurora's self-contained replica to perform our recovery plan, and we enabled multi-available zone deployment. So our data will first ingested into our writer instance, and then it will be replicated through the read-only Aurora RDS. And then all our future ETL part, the modeling part, its data source will come from our read-only replica. And then you can see that there are some snippets from our project in experiment. Our data flow will from the RDS raw data tables, and then it will go to the more clean features enabled silver data bucket in our S3. And then after the full ETL part, it will go to the, and also it will, through our modeling part, the data will flow to our recommendation output data bar 3. And then after we perform the whole data pipeline, then it will extract the recommendation results back to our RDS table. And then I will hand over to our team member, Charles, to explain to you the more detailed ETL part.
Oh, thanks, Charlie. This is Charles, and I will tell you about the procedure of the ETL in our INBA project. So the next ETL is a crucial step for our INBA project that involves extracting and transforming our data from RDS read-only replica and loading it into the S3 bucket as a self data. The ETL process we do can be broken down into the following parts. We first established a connector to the RDS using the JDBC, which allows the glue to subsequently read the data out of the RDS database through the connector. And then we use the glue crawler, which helps us to automatically find the metadata information for crawling and updating the data in the glue's catalog. And in catalog, we process and manage the 5 corresponding transactional tables. These include aisles, department, products, orders, and order product. And then next, we built Glue's ETL process, and we built the Spark-based Glue job to transform the information into the 5 tables by constructing the more detailed more detailed and meaningful data features, and we then store the processed data into the S3 bucket as self data for subsequent machine learning modeling. And apart from the above, considering the accessibility and the security of the data, we created and configured the IAM role in our VPC with only glue access and S3 access to do the ETL work. And some partitioning can also be set up in this ETL procedure. Next page, please. And on this left-hand side, our inbar crawler extracts data from the specific data source based on the provided configuration and rules. Additionally, it can monitor the data source for any changes and automatically update the metadata and data catalog accordingly. While on the right-hand side, you can see the screenshot of the scheduled glue ETL Spark script. And in this script, we generate a dynamic frame for the catalog as required and employ a series of operations to write the data to the designed destination. So next, I will hand over to Sun Yan, who will tell you how to do the next step of the machine learning modeling after getting the ETL data from S3. Thanks.
Okay, thank you, Charles. Now I'm going to talk about data modeling. After the processed CSV file is generated and saved in S3 bucket, the first Lambda function will be triggered to start an existing SageMaker notebook instance. Once the instance is in start status, it will automatically run the Jupyter notebook in the instance. It is implemented by using SageMaker lifecycle configuration. We write a bash script with control type in lifecycle configuration so that it can execute all cells in the notebook or one instance starts and monitor the IDLE time of the instance and the kernel for every 5 minutes. If the IDLE time reaches 10 minutes, the instance will automatically shut down. And we use SVD as our machine learning model. It's a built-in metric factorization-based model for recommendation system in a Python library called Surprise. It's an abbreviation of simple Python recommendation system. In the output of ETL process, a new column is generated by dividing product sequence 1 by 2. We call it recorder probability, which indicates the probability that the user wants to purchase a product again, and the value ranges from 0 to 1. In order to use the SVD model, we further process the recorder probability column to categorize into 5 ranks. For example, rank 1 will be the value from 0 to 0.2. Rank 2 will be the value from 0 to 0.2 to 0.4, and so on. Then user ID, product ID, and rank recorder probability is fed into the module to get the top 3 recommendation result. The result will be saved in JSON format and sent to another S3 bucket as a source of API call. Also, the result is written back to RDS in another schema called recommendation, so that a marketing team can use it for analysis purpose. And next page, please. Yeah, and this page is our part of code. The Lambda function on the left is to trigger SageMaker notebook instance, and on the right part, that's our code for machine learning. As you can see, we also use cross validation based on SVD module to get the minimum RMSE value so that it can make prediction more precisely. Yeah, okay. And the next part is James will talk about data serving.
Okay, thanks, Song Yan. So now the JSON file is stored in S3 bucket, and the data contains the key value pairs, where user ID is the key and a list of 3 product IDs is the value. Now, end users may have different ways to trigger the recommendation process. For example, when user log in the app, then our post API called get product will be called where the query header is the user ID. And then the Lambda function will be triggered when there's an incoming API call. It fetches the user ID from CloudWatch log group, search for the latest JSON file from S3 bucket, and read the file to get the recommendation product IDs. And finally, the Lambda function returns the product ID back to the API gateway and received by the backend developer. Next page. So the left image is a screenshot of our API test, and it can successfully fetch data from JSON file in S3 bucket. And the image on the right is the Lambda function, including triggered by API gateway and fetch data from S3 and returns back the data to API gateway. Next page. Here we create a simple web page to simulate the process. So you can see when we enter the user ID, we can get top 3 recommended product IDs. For example, in the right image, user 2712 bought these products before, and the machine learning algorithm will calculate the estimate score, indicating how likely the user will buy the product again. And we take the top 3 products as our output. Next page. So now let's look at our extensive branch. It's for our learning the CDC process purpose. So it starts from the left. We use database migration service or DMS to implement the CDC process. The source endpoint will be the Aurora writer instance. And in order to enable CDC, we need to change one setting in RDS PostgreSQL parameter group, which is to change the RDS the logical replication from 0 to 1. The target endpoint is another S3 bucket to store data coming from DMS. Now, when we run the DMS replication task for the first time, it will load 5 entire tables in the database to S3 bucket in CSV format. And all subsequent changes made from database will be recorded as the structure in the below image. It adds an additional column to indicate whether the operation is an insert, update, or delete. And in AWS Glue, we first set up the crawler to crawl the table stored in S3 bucket when DMS loads the entire table for the first time. And we can see all data are loaded in a data catalog table by using Athena. Then every time the CDC file comes into S3 bucket, the Lambda function will be triggered to run the glue job, so that we can generate the latest table by merging the old table and the CDC file. Finally, the updated table will be stored back to data catalog table. By doing so, we can query tables from Athena directly, or we can use Tableau to connect to Athena instead. And in the future work, we may try to integrate the extensive branch into the main branch to make the whole pipeline complete. And thank you. That's the end of our demo. Any questions?